Hello, welcome to Lecture 8A in our series. This lecture is about unit commitment. This is the term that the power industry adopted, which basically says when are units on and off. And you will realize soon that we don't simply turn all the generators on and leave them on all the time until they're out of fuel or taken down for maintenance. We turn a lot of the units on for only part of the day and then turn them back off, and this is done for economic reasons. And you have to schedule enough generation to meet the load and to be safe, and we'll talk about what some of those things are. And we also don't want to put too many units on, because then we lose efficiency and it costs more. So here, for example, is a data for 3 generating units, and we have a unit that's 600, 400 that's 1,000, and one that's 200. So we have 1,200 maximum power that we can get from these 3 generating units, and I've given you their cost here, MBTU per hour, and I've given you their fuel cost. Wherever you see this R, it should be $sign. So we're going to now ask ourselves, what are the combinations to supply 550 megawatts? Just that much, 550 megawatts. So what I did was I put down all the combinations here, unit 1, 2, and 3. So I start out with all of them off, and then just number 3 on, and the other 2 off, and then number 2 on, and 3 off, and so forth. These are I'm just counting up to 8 in binary until I get all 3 units on. So this covers all the combinations, and it turns out, because I ordered the units with the largest here, second largest, smallest here, then as I go down this chart, I add one here, and then add one there, here, and then I add both of them, the capacity goes up. Now, if I had ordered the units differently, this wouldn't be that way, but it is very handy to show the combinations with the capacity going up like this. And so I can go from 0, where all 3 units are off, all the way up to 1,200, where all 3 units are on. Well, the first 3 states don't get up to 550 megawatts, so they're infeasible. I can't use any of those combinations. I have to have a different set. I got to have at least this combination is 600. Now, if it's going to supply 550, then I have to dispatch it. And you notice that I'm only going to dispatch unit 2 and 3. They're the only ones on. Unit 1 is off, so we put a 0 there. And the economic dispatch says load number 2 to its max, then put the remaining 150 to unit number 3. So now I have 550. And here's the 3 separate operating costs, and this is the final operating cost. And so I did that for all these combinations, and you see the economic dispatch right down here till the end, where I have 3 generating units operating. Now notice that all 3 generators operating happens to have the highest the highest total cost. The least cost, 5418, no, 5389, right here. So there is the combination that's the least cost, and that says just operate the first generator. That'll give you the least cost to supply that unit, that load. Now we'll come back later and we'll say, well, is that the best? In this case, yeah, that's the best from a cost viewpoint, but we'll talk about some other effects later. Well, now I'm going to take this this 3-generator system, and I'm going to have a simple daily load that starts out at 4 in the afternoon, and it's very high load. Then the load goes down in the evening, and at nighttime it's very low, it's flat, and then in the morning it starts up again and it comes back up to the same. This is very typical of load in power systems. It's high during the day, it's low at night, and it's, it keeps going from high to low like that. The highs are different for different days of the week. We'll see this at a slide near the very end of the second series on unit commitment. But the typically the load is going, and this is because during the day people are up, they're running things in their house, businesses are operating. Then at night people go home, the business is shut down, turn the lights off, turn the machinery off, and eventually people turn their lights out, and we reach a certain load during the night. In the morning, people come back, they start opening their businesses, the lights go on, they're cooking, whatever, goes back up again. Okay, and we've got this over a 12-hour period here, and here is this is 500 megawatts right here, and this is 1200. So if I'm going to run these 3 generating units, when I look at this, I can actually come up with a shutdown rule. Here is the load, and it's basically the load goes from min to max here. Okay, from 500 up to 1200, and if you want to supply 1200, you've got to have all 3. 1150, you still have to have all 3. 1100, all 3. 1050. Once you reach 1000, I can turn off this unit. So there's that unit going off. Now I run with units 1 and 2 and not number 3 all the way down to way down here. So now these 2 go off at 600, and I'm only operating on the first unit. I don't show 0 down here where you would turn all the units off. So this does not include the 0 state. So they call this a shutdown rule. It says, okay, as the load comes down, I shut unit number 3 off, then later on I shut number 2 off. I always keep number 1 on because it's the most efficient. And it looks like this. Here's my load, the curved line. So number 2 has to stay on, number 3 has to stay on here, as well as number 2 and number 1. So here's number 1. It's the crosshatch down here. Here's number 2 over in here, and here's number 3. So 3 can turn off once the load is below 1000, and then number 2 can shut off at 600, and number 1 supplies everything that we need. Later on, as the load comes back up over 600, I got to put number 2 back on, and then I have to turn number 3 back on. So this is a very simple way of doing unit commitment, is to just have a shutdown rule that people can apply. There are other aspects of unit commitment that we need to worry about. One of them is spinning reserve. And the spinning reserve says I need to have at least enough generation available. If I lose one generator, I've got to have room between the other generator's operating point and their maximum, so that if I lose one, the other generators can pick up. So let's say I have my three generators. Now with the 3 generators that we have here, no, we can't do it. So let's just go to a hypothetical 4 generator system, and I lose a generator that was whatever amount it was generating. Once that happens, the governors want to bring this unit up, and this unit wants to come up, and this unit wants to come up, and I need this much space. Okay, I need there and I need here. I need that much megawatts. If all 3 of the remaining units were already operating at their max, and I lost this 4th unit, then these couldn't come up. And the frequency would start to go down. Pretty soon the other generators would shut off, and the system would go dark. So we need to have this ability. It's probably better if I put little arrows here, see? So I've got to be able to bring the units up. And that amount of megawatts in there, it's measured in megawatts, is called the spinning reserve. Well, spinning because these units are on, they're synchronized, they're putting power into the system. If this unit goes off, I can't run to the plant next door and start shouting and saying, quick, put the unit on. Because the unit may need to take hours to come on, or even many minutes. It's got to come from units that are spinning. They're synchronized to the system and spinning, and the governors can bring them up. In addition, there's the fact that if I have a unit that can go up real fast like this, that's really good, like a hydro unit. But if I have a big steam unit, it may take a long time to come up, and I have to take that into account as well. Okay, other constraints: minimum up and down time, very critical. It may turn out that if I turn a unit on, I have to leave it on for so many hours. And these have to do with a lot of the operating constraints, temperatures within the unit, within the plant, and things like that. The turbines and various other effects. And they don't like you to turn it on and turn it right back off. Or conversely, they don't want you to shut it down and then try and turn it back on again right away. So, but this causes a lot of difficulty. We'll see this later on in one of our examples when we start to include the minimum downtime, that it can give us a very different unit commitment. Crew constraints are simply the fact that I may have two generating plants that share a crew of people, and they're close enough, and so it says that the crew has to be there to get the plant started, and then they leave a couple of operators and go to the other plant. Well, I can't be starting both of them simultaneously because the crew has to be at one or the other, so that's a constraint. Startup costs. This is interesting. It says the energy needed to bring a large steam generator online. So if I have fuel going into the plant, here's the fuel, F, and I run it into a boiler, and it ought to be pretty obvious that just turning on the flame, let's say it's oil fired or gas fired, lighting the gas doesn't produce steam instantly. That water takes a long time to boil, and eventually we get steam here. We run it through a valve. Here's our valve, and we run it into a turbine. And the turbine takes quite a while to start up, and we don't want to just blast all the steam in. We want to start running it gradually and let the turbine come up to speed and up to temperature inside the temperatures of the blades and so forth. There's very critical paths that it has to follow, and eventually it starts turning the shaft, and we have a generator out here. So between the time to boil the water and the restrictions on how fast you can start the generator and how fast you can bring the temperatures up inside the turbine, all of that restricts it, and it says that it takes a great deal of time. Now, the fact that it's going, let's say, for several hours, we're putting fuel in all during that time, and we're getting no electricity out. There's nothing coming out here. The P is equal to 0 until we've got everything running, it's synchronized, and then we close the breaker. But we're still putting fuel in. That fuel over this startup, over this period of time, is called a startup cost. It costs you something to bring these things up to temperature and get it up to speed. Okay? Hydro constraints, we're going to see this later on. Things like you don't want to put too much water into the downstream reservoir and have it spill. You don't want to run the water up over the banks of a river and things like that. Sometimes generators are what are called must run. It just it means exactly what it says. A unit must be on. Why? Why would a unit must be on? Well, that unit might be providing reactive support that's critical for a certain part of the system where that unit is located. Or they know that unit has to be on later on in the afternoon, so they put it on and they say it's must run in the morning. These are set by the operating people. Fuel constraints. Don't use more gas than certain pipelines can supply during certain hours of the day. Don't run out of oil in the tank that's supplying the power plant and so forth, things like that. Okay, the unit commitment solution. Now, if let's say that we have a pattern of M time periods, so we're gonna take time and we're just gonna chop it up. Usually, this is in hours, and a good example is the number 168, which is the number of hours in a week. So a lot of unit commitment runs are made over 168 hours. We'll put an H in there. N units. This can be in the hundreds. So this is a very, very complex calculation. There are different load levels that are there. We'll say that there's for each time period. We'll have a load. So here's our time, T, and we've divided it up, let's see here, into 4 hours. And here's load. And we're going to say the load starts here, the load comes up, the load peaks, then the load drops, let's say really far, then it goes back up. So this is the load L in megawatts. So there's my load in megawatts. And for each hour, there's a different load value. For each hour, there's a different load value. We're going to establish commitment if we did it by enumeration, okay, better known as brute force. The total number of combinations that we need to try each hour is like this. We need to try all N units one at a time. That you probably can't supply. Now, this doesn't say anything about feasibility of these combinations, but just to enumerate them all N units 2 at a time, all N units up to N minus 1, and all N units N at a time. There's only one of those. And this when you sum that all up, it's 2 to the N minus 1. Well, if N is 100, this gets to be a gigantic number. And to do it for M time periods, it's 2 to the N minus 1 raised to the number of hours. Well, in this example, we said M equals 24. If you only have 5 units, the number of combinations times M, or to the M power, is 6 times 10 to the 35. So you can see that the number of combinations just gets to be huge. Gets to be very, very big. By the way, those of you that have had probability theory and combinatorics would recognize this formula. It says that Cnj is n factorial over n minus j factorial over j factorial. Very, very big numbers. Here are the techniques that we've used. Priority list is very similar to the shutdown rule. We're going to show you an example of a priority list scheme. This one you can do basically on a piece of paper. You can do it with a spreadsheet if you wanted to. Dynamic programming was invented in the late 60s, early 1970s, and used for maybe about 10 years. Actually, some people probably are still using dynamic programming, so we want you to understand how that operates. That was one of the first really comprehensive forms of unit commitment. Lagrange relaxation came in the late 1970s, early 1980s. There was some work that had been done at MIT on Lagrange relaxation, and it gave us even more improvement in the solution. Lately, there has been advances in the art of computer programming to be able to solve what are called large integer programming. It's a very, very difficult kind of program. We've talked before about linear programming and dynamic programming. Integer programming is a very, very advanced topic, and integer programming is there are codes now. There was some code developed called the Cplex program. There are others, and now those are starting to be incorporated for unit commitment. And this is considered probably as close as you're going to get to the absolute best combination that meets all of the constraints, is integer programming. So here's the priority list scheme. We take our 3 units and we say, where's the average production cost? So we got, here's the best, here's the next, and here's the third. And so we're just going to say we're going to order them unit 2, unit 1, unit 3, 2, 1, 3, and then we're going to say, okay, unit 2, because you're the best, so any combination that's 100 up to 400 is unit 2. Then from there we're going to go with unit number 1 and number 2, so we can go up to 1,000, and then we're going to go from units 1, 2, and 3 to get up to 1,200. Then that's the priority list scheme. Can be done on a spreadsheet. You can just build a spreadsheet and then order them and tell your people, okay, you just look at the numbers here and follow it. Okay, dynamic programming. Remember we had a diagram where we had this represented stages across the land, and we put some lines down here, and we said here's stage 1, 2, 3, and so forth, and we said we went from one point to another, and we found the optimal path. Well, we're going to do unit commitment that way. In this case, there was only a cost to go from this state to this state. There was only cost going from one state to the next, and then from this state to this, there was a cost this way. In dynamic programming for unit commitment, we add a little more complexity now. Each state is represented by a dot. The dot represents one state operating during one time period. So here's our time periods, and we could say, well, okay, here's we're going to divide the time periods up like this. So I've got 3 time periods here, and these represent states, and so I generally will have multiple states over here, but I haven't drawn all of them. I've just drawn the black ones in here on the slide. It says that we're going to start here. We're going to go down this path until we get to this one. Well, at this state, it represents a set of generating units supplying the load during this time. So later on we'll call this, for example, K minus 1, and we'll just call this K. So during the K minus 1 period, there's a load, and this represents a certain combination of units. Stick with me, we'll get to that on the next slide. This represents a set of generators, and so those generators supplying the load during that hour. P, that's the production cost, okay? P is the production cost for that combination to supply the load at that hour. The S cost is only going to come in if there's a startup cost. That's the transition cost. It's not like over here in the travel, where we're paying a certain distance cost. Here it represents a startup cost. So in sometimes from this combination to this, or if I'm starting a generator, then the startup cost, otherwise it's 0. And then there's another production cost at the end. So let's say we start out, and it always comes out like this, where F cost is the accumulated cost. So I start out with a production cost, then I add a startup cost, And a production cost here gets added to this, so I'd have a production cost, a startup cost, a production cost. And I'm accumulating these in the F cost. Then I go and I add a startup cost and a production cost to the F cost. And so down here at the bottom, I have this final equation, which is the F cost at the end of the path over here. Let's just say we're going to go from here to here, up here. So the F cost here is equal to the P cost at the start plus the S cost, the so-called startup cost across here, plus the F cost. Well, whatever that F cost was to get up to the end. By the way, this should have said end. I'm sorry. This should say end. End of path. So I'm taking I've got an F cost, and I keep updating the F cost. And we're going to see that by dynamic programming, I could be going up this path, I could be going over this path. From here, I could go here, just like the travel one. And then I could come down, and I could, you can see that it's very similar to this travel one that I did up here, where I was just looking at distances or tolls along the road. It's the same thing, only I've got production cost at each state, and I'm accumulating those production costs, and I'm trying to get to the minimum of this. So really, unit commitment says, get me the minimum production cost to get to the final hour. So here's an example now where I took my 8 states. I didn't put the 0 state. Yes, I did. It's right here. So I called that state number 1 to state number 8. And my capacity goes 0 up to 1200. And each of these combinations has a dot for each hour. So here's the time over here. Okay, here's the time over here. I'm not going to draw big vertical lines, but there's 4 time periods. And the time period goes across the bottom here, and there's a load. So there's some load function that says, well, the load is like this, and then it goes like this, and then it peaks, and then it goes back down, and so forth. So there's a load for each time period, and we've given you that in numbers in here. You can see that I drew it a little different than the numbers, but in any event, there's a specific load for each hour, and every hour could have any one of these combinations. So I have a dot. I have 8 dots in each hour. Well, this particular path says I started out with all 3 of them on. Then I turned off. I turned off number 3. Then I came down here and I just had number 1, and then I turned number 3 back on. Now that's a path that represents a unit commitment schedule. The schedule says it goes from this combination to this combination to this to this. The simplest combination is this: never turn anything off. Okay, so you just run across this way, and the problem here, where dynamic programming runs into trouble, which should be obvious, is that from here, I can go there, I can go there, I can go down here. Now, some of these represent infeasible states. If this is 800, well, once I get down below here, these, I should say, well, these are all infeasible. But if I'm just doing brute force enumeration, let's enumerate them all, and so there's all the transitions from this first state. Okay, if I were in this state to begin with, I got to do it all over again. You can see me adding the lines to the figure. Well, how many lines are there in there? How many transitions? There's 8 times 8, or 64. And then I have another set, that, et cetera, et cetera. I would have all the transitions like this. So I would have 64 transitions here, here, and here. Well, I don't want to do 64 separate calculations of S and P cost and F cost. I can't afford, even if they were feasible, I don't want to do that. So we have various techniques, what we call a reduced search range. So here at our K-1, I'm only going to search over the set L, which has n members, which I just crossed out, n members. That's set L. And over here, we're going to have set, which later on we're going to call this set I. And so that's the set I. So we're going to go from combinations in L to combinations in I. Well, n here is only 3. And in here I'm looking at 1, 2, 3, 4, 5. And then when I go to the next hour, where I'm going to go from K to K plus 1, I'm going to go from 3 in here to 5 out here. I pick the best 3 and I go out to 5 and so forth. Now these reduced search ranges drops the complexity. Well, 3 times 5 is 15. That's a lot better than 64. And then 15 again. So I'm really cutting the work down. And if you're getting suspicious, you're correct. As soon as you start doing that, you're not doing a full enumeration. You might not hit the optimum set of paths. You might not hit, and very likely you won't hit, the optimum unit commitment. So dynamic programming, we had to take shortcuts in order for the computers to be able to solve the problem in a reasonable time. When we run this unit commitment, even if it took an hour of computer time, that would be okay, but we can't let it take weeks. Okay, we need the answer in an hour, let's say. So we have to do that. So we say that it reaches a suboptimal, not necessarily optimal solution. So here's the now I put this this on here, this thing here. It says in when we see this up here in parentheses, the first is an hour and the second one is a combination. So we're going to say, okay, the cost F. Now that's the accumulated cost at our K. Remember, we're coming in this particular thing. We're coming up to K from K-1, and we're going to say minimize over L. Now remember, that's the set. L is the set of units that I'm looking at here. That's L. That's the set of combinations. They don't have to stack up 1, 2, 3 like this, but 3 states. So we're going to go over L. We're going to look at each set of transitions from the units combinations in L over to K. And so then we're going to look at the first off, the production cost that's at our K, and it's part of this. Remember, we said here we're going to have a set, and we used 5, so I'll do that again. And here's the set I. Okay, there's the set I. And we can put these brackets around it. So there's the set I. So I'm going to look at all possible paths from each member of L to each member of I. So there's 15. So I got to run this calculation out 15 times. And I'm going to, each time when I get over here, I'm going to record the minimum over the set L. So when I get to this one, I want to know, was the minimum path from that state or that state or that state? So that's what it means here, minimum over L. First I add the production cost at this point, at this end, then the startup cost to go from K-1 in L to K in set I. And then last of all, each of these would have had an F cost, F cost. So I add the F plus the startup plus the P cost, and that's the total cost to get there. And I do it for each. So I would do, for example, I would do this, then I would do this, and then I would do this. So I've got 3 paths to get to this one, and all I want to know is which one was the cheapest. And let's say it was this one in the middle, so I will remember that one. We'll put an asterisk there. And that one is the only one I care about. And remember when we did DP, we said, okay, when you're coming back and you get to this point, well, then you know what path to take. And that's the way we go forward through this, and then we remember the paths, and we have our optimal path. So we have to execute this recursive algorithm over and over again. And this is a flow chart. We do the F cost. We do it at the start at k equals 1. Then we increment k, and we say, well, L is the set of feasible states in interval k minus 1. And here's our long equation in there, and we find the minimum over L, and we do this for all states I in period k. Save the lowest cost strategies. If it's not the last hour, we increment k again. So we're just jumping from 1 hour to the next, and we're looking at all these possible paths that we talked about before. And that's basically the execution of that recursive algorithm. So here's an example. You really should look at this in the book. It's kind of a long set of things to go in here. By the way, these R's should be dollar signs. I'm going to put this down. R should be a dollar sign. Okay. We have 4 generating units. We have we gave you all the details about the so-called no load cost. I'll explain that in a minute. Here we have some of this real tricky stuff of minimum up and down time. Oh, we put that in there too. So this generator, number 1, if you put it on, you have to keep it on for 4 hours. If you turn it off, you have to keep it off for 2 hours, and so forth. Here's the initial condition. Number 1 has been off for 5 hours. 2 and 3 have been on for 8 hours, and 4 has been off for 6 hours. Here's the startup costs, and if it's hot or cold start, it just says it's considered cold start if it's been off for at least 4 hours. Here's the load, 455. It peaks at 600, it drops back, and then it goes back up again. We'll see a picture of that in a minute. Here's the way we calculate the operating cost. Very simple, linear. We have a constant, so it's this no load cost plus the incremental cost, or the slope, times P, times the P, the output, and it has to be between the min and max. That's very simple, linear, and if you remember back to economic dispatch lectures, you can just stack these up in memory by incremental costs, and you can do the dispatch very simply. So here we go again. We've got states. Remember, these are the combinations. Now here we have 16 of them, all the way down here to nothing on to all of them on. And here's the load, up to 690, from 0 to 690. Okay, so these are the unit combination. Now A, 1 equals on, 0 equals off. That's just a notational. Okay, and case 1, strict priority order. If I do a strict priority order, remember I order them up by the best average operating cost at the maximum. So here's the best unit, then the next 2, then these 3, and then those. So that's the strict priority order. Here's the megawatt breakpoints. You can go ahead and solve this by a strict priority, and we'll show you a plot of that in a minute. Complete enumeration says I'm going to do, now let's come back here. That says that for each hour I'm going to do 16 transitions to 16 others. 16 times 16 paths. Well, that's not that long a calculation, and we did it just to show what the answers would be. Here's a typical calculations. This is my my recursive formula again. So if I'm going to go from hour 0, L is equal to 1, is equal to 12. We said that's the initial condition, is state number 12, which is this. The second and third units are on. And so then I'm going to go from to the j equals 1, the first hour. Then it can be, these are the states that we can look at, and we're looking to the second hour, and these are the feasible states there, 12, 14, and 15. So here we can go 15, 14, 12, and you get the minimum cost, and we record that minimum cost as the best path. So here we are. We're starting out here, and here's the load. See here, I said I would draw the load. There's the load. I'm just tracing it right now with the red marker on the screen. There's the load. It comes down and then it goes back up. And case 1, priority order. That's the solid line. It says you keep the second and third units on. Here you have to put, so then it says put the first unit on, then take that unit off, then you keep everything on again for another hour, then you drop it to just the third unit, and then you come back up here to the original state. That's the strict priority order. If I do case 2, complete enumeration, in this case it figures out that it doesn't have to go up here, it can go here. I'll use the other pointer. It doesn't have to go here, it can go right here. So it's slightly different, otherwise they're the same. Otherwise, so you can see that priority order, in this case it's not that bad. Now, minimum up and down times, case 3. So here I'm going to do complete enumeration again, but I've got minimum up and down times. And what happens is I can't shut this unit off because there I shut them down. So they're down for 1, 2 hours. Oops, I want them back on. But that's violating the minimum up and down. So the optimum path says you got to leave it on. You got to leave the second and third units on. I could turn this fourth unit on, and then turn it back off. That one worked okay, but this one wouldn't allow me to shut down. So the minimum up and down rules affect the operation very strongly here. Thank you very much.